So here we're going to do sample problem 2010. As I mentioned in class, I wanted to run through this. And basically, in this problem, we are given a reaction, which is, again, the oxidation of sulfur dioxide, basically a reaction of sulfur dioxide with oxygen to give us sulfur trioxide. And then this is taken on and used in the production of H2SO4, or our sulfuric acid. Now, what we're given then is three problems to solve related to this reaction. First, we're asked to calculate the equilibrium constant at 298 Kelvin. We're given the standard free energy change for 298, and that would be negative 141.6 kilojoules per mole of the reaction, as is written here. And then we're asked, and then using enthalpy values and entropy values at 973, a standard free energy change has been calculated at that temperature of 973. And this was done basically using enthalpy and entropy values. So we've got this standard free energy change at 973 of minus 12.12 kilojoules per mole of this reaction. Now, what we're going to start with is we'll start with A, we'll do this, and then basically we'll go to B, and we're given some pressures of the gas, basically of the sulfur dioxide, the oxygen, and the sulfur trioxide. One reaction, there are two containers. One reaction is going to be run at 25 degrees, which is our 298 Kelvin, right? So 298 Kelvin. And the other will be at 700 Celsius, which is our 973 Kelvin. And we're asked which reaction, in which direction will the reaction proceed to reach equilibrium at these two temperatures. So we'll go through that. And then we're asked finally to calculate the actual free energy change for the system in part B at each temperature. And so here we'll go through and we'll start with part A. We'll tackle that. So basically our plan for A is that we know the standard free energy change, the temperature, and the universal gas constant, so we can calculate K at each temperature. And then we'll use the conditions that we were given in part B to find out whether or not the reaction will go in the forward direction or the reverse direction. So we'll calculate Q and then compare that to K's. And then we'll do we'll do our actual free energy at each temperature using this equation here. So let's start off with A. And basically, remember, we have defined for us the standard free energy change is equal to minus R times T times the natural log of K. And so what this means is that to solve for K, we basically divide both sides by negative RT. So we're going to get delta G divided by RT. And then we raise both sides to the E, or we take E to both sides. So E to the natural log of K is simply K. And then what we wind up is E to the minus standard free energy change divided by R times T. So what we can do then is at each temperature, we can just calculate this guy right here for each temperature, each particular temperature here. So let's start off with at 298 Kelvin. We've got a negative delta G standard divided by RT, and then that would be equal to a minus 141.6 0.6. I'm going to go ahead and convert this into joules. So this will be times 10 to the 3 joules. And that's because our gas constant is given in joules, 8.314 joules per mole Kelvin. And we're going to multiply times 298 Kelvin. And if we carry out this calculation, we can see our kelvins are going to cancel here. And our joules are going to, I'm sorry, this is joules per mole. And so our joules per moles are going to cancel here. And we're going to get our equilibrium constant. We're going to get the value of our exponent for our equilibrium constant. So that would be 57.2. And so to solve for K, we will get K is equal, K298 is equal to E to the 57.2, which gives us 7 times 10 to the 24. So that would be our K at 298. So let's go down, and we can now solve for our K at 973, but first we'll set up this part at 973K. We're going to have our minus delta G standard divided by R times T, and we're going to then calculate this in this way, a negative 12.12 times 10 to the 3 joules per mole. And we're going to divide by 8.314 joules per mole times Kelvin. And we're going to then multiply by 973 Kelvin. And then we will calculate. So if we carry out this calculation, we get 1.50. And so our Kelvin, our equilibrium constant at 973 is equal to E to the 1.5. And let's see, that will then be equal to 4.5. So our K, we have our 2 Ks at each of those temperatures. Okay, then we have, now we have gotten our 2 Ks, so we're ready to go to part B. And so for part B, we actually need to calculate the value of Q using the pressures that we were given. And so we'll set up our Q this way. It will equal to the pressure of our SO3 squared divided by the pressure of our SO2 squared times our pressure of O2. And so if we plug in the values that we have been given, we get 0.1 squared divided by 0.5 squared times 0.01. And if we carry out that calculation, we get a Q value of 4. Now, what we see then is Q is less than K 298, and it's less than K 973. So it's less than both of them. So the reaction will go to the right, or will go forward. right, or it will go to the right. Okay. So basically at 298, the system is far from equilibrium and will go far to the right. And at 973, it is fairly close to equilibrium, as we can see here. And it still will go to the right, even at the much higher temperature. Okay, now part C then asks us to determine the actual free energy change at each temperature using the equation for the actual free energy change. So we'll start with the equation for the actual free energy change, and that would be delta G is equal to the standard free energy change plus R times T times the natural log of Q. And at 298, we'll do first, we would get our standard free energy change, which is minus 141.6 kilojoules per mole of reaction. And we're going to add our 8.314 joules per mole times Kelvin. We're going to go ahead and multiply this times 10 to the minus 3. I'm sorry. Let me correct this. Correct that. That would be 8.314 times 10 to the minus 3 kilojoules per mole per Kelvin. And then we'll multiply times 298 Kelvin. And then we'll multiply times the natural log of 4, which is our Q that we calculated earlier. And if we carry out this calculation, we'll get an actual free energy change of minus 138.2 kilojoules per mole. So that would be our actual free energy change at this temperature. And then using the same equation at 973, of course, we'll use a different temperature, but we'll use the delta G at 973, which was given to us as minus 12.12 kilojoules per mole. We will add again our 8.314 times 10 to the minus 3 kilojoules per mole per Kelvin times our 973 Kelvin times the natural log of 4. We carry out this calculation, we get a negative 0.9 kilojoules per mole. Now, we look at this and we what we would see is basically that the actual free energy change at 973 is quite a bit smaller, so we are very close to equilibrium. But why use this such a high temperature when the processes with this kind of actual free energy change is only barely spontaneous? And it turns out that basically, remember, when you heat up a sample, you have more of the molecules that are going to be above the activation energy in terms of temperature. And so what you're doing is you're heating up the reaction to make it go faster, because if the closer the molecules are, the more molecules you have that are above the activation energy in terms of their thermal motion energy, then the reaction will go faster, even though it will only proceed a small distance to the right. It still will go quite a bit faster at higher temperature. And you also, in this industrial process, they also will use a catalyst. So they use higher temperature and a catalyst to attain a higher rate. Even though the amount, you're very close to equilibrium with this type of actual free energy change. You still are to the left of equilibrium, so the reaction will proceed forward and you will generate SO3. And of course, in a process, if you're making the SO3, but then you're using it up with a subsequent reaction, well, then more SO3 could be continuously made. So that's another aspect just to keep in mind. But that is this problem sample 2010, all 3 parts. And that is all I need to say about that.